Okay, hello, welcome to my channel. Now in this video, we want to talk about the conjugate of a complex number, alright? So if you are given a complex number, let's say z being x plus iy, where x and y are real numbers, and of course I is the square root of -1, then the conjugate of that complex number is in this form, x minus iy. So what we do is that to find the conjugate of a certain complex number, you just have to negate the imaginary part of that complex number, right? So if we denote the conjugate of the complex number z, denote it by z with a bar on top, with just a little line on top, or sometimes some people can use a star, maybe some text, or some people, right, can use an asterisk. So z to the some, so any of that, but in this video we're going to be using this one, z with some bar at the top. That means that the conjugate of a complex number z, represented by z with a bar at the top, is going to be x. Then in this plus iy, we're going to negate that imaginary part by using negative iy. Good. Well, this in conjugate of a complex number is just a reflection in the real part, okay, of a complex number. So this is how we can visualize it. So if we have let's say x and y, let's assume the both of them to be positive. That is, given a complex number z, let's assume x and y to be positive. And from our last videos, we've talked about representing a complex number on a plane, where we can use the coordinates x, y to denote the point or the complex number on a plane. So if this is x right here, and then this is y over here, all right, good. So x, y will be somewhere here, which is going to be the complex number z. So that point is the point x, then with the second coordinate being y. Good. So that is it. So maybe let's connect this like that, and then we have that to be like this. Good. Now you observe that its conjugate has the real part to stay the same, but the imaginary part has been negated. So instead of plus iy, it's now negative iy. So we're going to look at negative y, which is going to be down below, and then we are going to put these points to be here. So you notice that this right here represents, we can say that this right here represents the complex number z. Alright, in this case, I'm not talking about the modulo, so let's just take that to be the complex number z. And then this coordinate is going to be x and then negative y, which will now represent the conjugate of that z, which we call z with a bar at the top. Alright, good. So this is a reflection about the real axis of this complex number x plus iy, and that is the conjugate of that. So in fact, if a real number has only if a complex number has its complex part as 0, its imaginary part as 0, the conjugate will be the same thing as the complex number. That is, if the imaginary part of the complex number is 0, then the conjugate of that complex number stays the same as the complex number itself. Because if the imaginary part is 0, we just have a real number, and there will be no reflection about the horizontal axis, or in other words, about the real axis. Okay, that's very nice. Now let's clean the part of the board, so that we are going to talk about some properties of the conjugate of a complex number when it comes to maybe two or more complex numbers, where we can have the product of a complex number with a conjugate, what it looks like, the sum, and other operations involving a complex number with its conjugate. And it's going to be a very nice one. So let's just clean it off, put the properties down, and we are going to prove each of them. So let's see what we have. Okay, so we have to prove the following properties. All right, now start off by saying that let z be x plus iy, the z1 be x1 plus iy1, and the z2 be that. So these three are complex numbers. All right, then the following properties hold. Now we have the first property here, which tells us these two bars at the top means if you take the conjugate of a complex number z and take the conjugate of that conjugate, you're going to get the complex number back. So what that means is that taking the conjugate of a complex number 2 times, you're going to get back the original complex number. Now, given that z alone is x plus iy, x plus z alone is x plus iy, okay, the conjugate of z, which I'm going to represent it using z with a bar, right? So let's say z with a bar is going to be what? Well, that will be the conjugate of the complex number z, which is going to be x minus, right, iy, just by negating the imaginary part. Good. That is the conjugate. Now, what happens to the conjugate of that conjugate? So let's say this is the conjugate, and then we take the conjugate of that. In other words, we are going to negate this imaginary part again. Okay, that would give us, well, x, then the negative of, okay, negative iy, which is the same thing as x plus iy, which is the original complex number z. So that shows that the conjugate of a conjugate of a complex number is the complex number itself. So that's the z over there, and that's a box that I wanted to shade, but I messed it up. Okay, great. So let's look at the second one real quick. So for the second property, we have to show that when we take, sorry, this is supposed to be this way. When we take the modulus, that is the modulus, of course we talked about it already, the modulus of a complex number z, okay, is the same thing as the modulus of its conjugate. So you notice that given a complex number z, that the modulus is going to be, well, from the definition is going to be the square root of x squared plus y squared. That is the square root of the sum of the squares of the two parts. So that is x squared plus y squared. That is the modulus of a complex number z. But you notice that the conjugate of the complex number z can be written as, is going to be x minus iy, of which its modulus will be x squared plus the imaginary part squared, that is negative y squared. Okay, so let me put it out here, negative y squared. Good. But this is x squared, and then negative y squared is something as y squared because the square will evaluate the negative sign. And this right here gives us the modulus of z. So that tells us the modulus of the imaginary part, sorry, the modulus of the conjugate of the complex number z is something as the modulus of z. Good. Okay, so that's it for the second one. So again, you draw the box and try to shade it properly this time. But it's not really nice. So let's see the third one real quick. Well, the third property tells us that if you multiply a complex number by its conjugate, you will get the square of the modulus of that complex number. So let's see what we get. We multiply the complex number z by its conjugate z bar. That would mean we're going to multiply this by its x, that place, where that place will change to minus. So this x plus iy. We multiply it by x minus iy. Alright, so let's see what this will give us. Whether it's going to give us the square of the modulus of the complex number z. So you multiply x times x, that will be x squared. Then you multiply iy times negative iy. Well, you notice that I here and I here, the product of I and I will give us negative 1. With this negative, that will become positive y squared. Okay? Then the next thing is to multiply x with negative iy. That will be negative ixy. Similarly, iy times x, that will be positive ixy. But these two are equal in magnitude and opposite in sign. So the result here will just be x squared plus y squared. But this right here is the same thing as the square of, this right here is the same thing as the square of the square root of x squared plus y squared, right? We can write x squared plus y squared as the square of the square root of x squared plus y squared, which is the same thing as the square of the modulus, right, of the complex number z, since the square root of x squared plus y squared will give us the modulus of the complex number z. And that's it. So we've shown that, so we can draw the box and shade it. All right, good. That's the third property. So let's go to the fourth one. The fourth one tells us that the real part of the complex number z is the same thing as z plus z bar divided by 2. Actually, this fourth property should be in two parts. It should be in two parts here, where we can also have an expression for the imaginary part. So let's just do this one and see what we get. So the real part of this complex number z, it can be written as z plus z bar divided by 2. But what is the real part of a complex number? The real part of this complex number is just x, right? So we know that the real part of z is x. So you want to show that x is the same thing as z plus z bar divided by 2. That is the complex number plus its conjugate. You take half of the sum. Good. But you notice that this x here can be written as 2x divided by 2. That is, we multiply the x by 2, and then we divide the 2 we just multiplied. That's very nice, isn't it? And I'm going to do addition of 0 to the numerator. So this is it. I'm going to add iy and negative iy. So this is going to be 2x. We're going to subtract iy, and then we are going to add iy to that. Okay, so we still have divided by 2 here. Well, let's see. This is going to be, let me split this into 2. 2x can be written as x plus x, right? So I'm going to take the first x. I'm going to take minus iy. Then I'm going to take the second x, that's plus x. Then I'm going to take the plus iy. Yeah. Then we divide this by 2. Well, as you can see, this right here is x minus iy, which is the conjugate of z. Okay, the conjugate of the complex number z is x minus iy. We add it with, so this is the main sum now. I'm taking this in 2. X plus iy, which is the main complex number z divided by 2. So what we've shown there is that the real part of z, all these equality signs leads us to this. Good. We can also do that for the imaginary part. In fact, this will be a good work for you. I want you to show that the imaginary part of a complex number z, which we can denote it as the imaginary part of a complex number z, can be written as, let's see, there are half of, not really half, z minus z bar divided by 2i. Yeah, so when you take the difference between a complex number and its conjugate, then you divide the result by 2i, you will get the imaginary part of z, which is going to give us y. Good. So you just check that out, all right? Let's do the fifth one. The fifth property tells us that if you take the, now, you also do one of these. This is, if you take two complex numbers, let's say z1 and z2, and we either add them or subtract them, all right? And then we take the conjugate of that sum or difference. The result will be the sum or difference of the conjugate of the two complex numbers. So let's do for one. That is, if you want to take the sum of two complex numbers, what this property tells us that the conjugate of the sum of these two complex numbers is going to be the sum of the conjugates of those two complex numbers. So you will do for the difference, all right? Yeah, you're going to use the exact same method that we'll be using here, so you watch out. So first of all, we'll add the two complex numbers together. So when we add z1 to z2, what do we get? Then we take the conjugate as a result. So let's see. Well, z1 plus z2, z1 is x1 plus iy1, and then z2 is x2 plus iy2. So adding two complex numbers, you add the real part of the first to the real part of the second, and then the imaginary part of the first to the imaginary part of the second. So we're going to add x1 to x2, that will be x1 plus x2. Then we're going to take I common, so we're going to say plus I common, then we add the imaginary parts together. So that'll be y1 plus y2. Good, great. Now you see what we have from here. Well, the conjugate of this sum will be when we change the imaginary part of the sum, right? That means we're going to have x1 plus x2. We subtract I times y1 plus y2. So after taking the sum, we now take the conjugate of that sum. But we are going to rewrite this a little bit so that we have x1 minus iy1 after expanding minus iy1, okay, minus iy1. That is the first part, this minus that. Then we're going to take x2 minus iy2. That will be plus x2 minus iy2. That is the second part, all right? Good. So after adding them together in that manner, you observe that x1 minus iy1 is something as a conjugate of the z1, okay? That is the conjugate of the complex number z1. We add it with, well, the second one will just be the conjugate of the complex number z2. That is z2. Good. So from the extreme left hand side we have this. To the extreme right hand side we have that. And we have chains of equality sign, which means that the conjugate of the sum of two complex numbers is something as the sum of the conjugates of those two complex numbers. And this works for the difference as well. That is where this is minus, that will also be minus. And you can also show that using the exact same steps, all right? Okay, great. So what we'll do now is to clean from the top everything here so that we continue with the number 6. So we've shown that this is true from here, all of these, we've shown all of them. So we're going to show the 6th and the 7th properties. So let's see what we have. Okay, now the property number 6 tells us that when we take the conjugate of the product of two complex numbers, the result will be the product of the conjugates of those two complex numbers. So we are given the complex numbers here to be z1 and z2. Good. So let's see what we have. Now the conjugate of the product of z1 and z2, right? That will be the conjugate of, well, we put out z1 and then put out z2. That will be x1 plus iy1. That is z1. You multiply it by x2 plus iy2. Good. So to multiply two complex numbers, we just expand the brackets. That will be x1 times x2. So you put it down here, x1, x2. Then we are going to multiply this and that together. That will be negative y1, y2. And the negative is because I is the square root of negative 1. So we multiply this part with that. We're going to get a negative y1, y2. Great. Okay, and that will give us the real part. Then the next thing is to multiply x1 with this term. Well, the I will be out, and you're going to see x1 times this term will be x1, y2. Then iy1 times this term will be plus x2, y1. This 2y1, and the I is taken common. That's it. Okay, great. Now let's see what we have. Well. We're going to find the conjugate of this complex number, of which this is the imaginary part. And to find the conjugate, we're going to negate the imaginary part. By that, we're going to have x1, x2 minus y1, y2. We take the negative of I times, so let's put it out here, x1 y2 plus x2 y1. That's the conjugate. So the line, the bar at the top is no more there. Then the next thing is to try to show that that will be the same thing as the product of the conjugates of each of those complex numbers. Well, we can continue and see how well we go. So this is what I'm going to do. I'm going to take this term and then this first term together. That will be x1 x2 minus I x1 y2. Then we're going to take the second term minus y1 y2 minus I x2 y1. Great. So let's factor out the common terms in each of these. So we're going to take this and then we're going to take that, right? So maybe there's no point putting the bracket. So we're going to factor out the common terms, and as you can see, the common terms in these first two terms is x1. That will give us, well, when we factor out x1, we're going to have x2 left, then minus, factor out x1 from here, that will be I y2, right? Then similarly, we can factor out the common term here, but I'm going to factor out negative I. So that when I factor out negative I, this term here will become, let's see, that will be negative I y1, sorry, negative I y1. The thing is, y1 is common, but I just want to factor out negative y. It's going to be like a better way or trick to just get us to where we want. So we factor out I1 from here. I1 will no longer be here, but we factor out the negative sign as well. So this is supposed to be y2, but we factor out I. So when you multiply this by negative I, you're going to get 1, which means the remaining here will be negative I y2. Okay, similarly, the negative I is out here and the y1 is out here, so we have plus x to left here. Great. So you notice that, well, this inside this bracket, this part and this part are exactly the same. This is x2 minus I y2. This is x2 minus I y2 as well. So we're going to factor out the common factor, which is this is a common factor. We're going to factor it out. We'll be left with x1 minus I y1. Okay, we're going to multiply it by x2 minus I y2. Great. But you notice that this right here is the conjugate of the complex number z1, and then this right here is the conjugate of the complex number z2. And what we've done there is that we've shown that the conjugate of the product of those two complex numbers is the product of the conjugates of those two complex numbers, which means that the mass 6 property has been shown. That's very nice, isn't it? Okay, so let's check the number 7 property. Okay, so we have the number 7 property to take care of. All right, so we want to prove that the ratio of this, the conjugate of this fraction is the same thing as the conjugate of the numerator. Okay, so we have the number 7 property to prove. Okay, so we want to take show that the conjugate of z1 divided by z2 is the same thing as the conjugate of z1 divided by the conjugate of z2. Great. So this is what we're going to start off with. We're going to start off with this fraction z1 divided by z2. Then we see a different way of representing the ratio before we take the conjugate. So we have z1 here divided by z2. But you know that when we want to divide two complex numbers, okay, the standard method is to multiply top and bottom by the conjugate of the denominator. So I'm going to multiply the numerator by the conjugate of the denominator, and then multiply this by the conjugate of the denominator as well. So this is the fraction line, while this is the conjugate of the denominator. All right, great. So let's see what we have. Sorry, the conjugate of the denominator. So at the top we're going to have z1 times z2 bar. So that's z1 times z2 with the bar, that's the conjugate of z2. Now at the bottom we have z2 times its own conjugate, and we've proven that already, that when you multiply a complex number by its conjugate, you get the square of the modulo of that complex number. That means we're going to get the square of the complex number z2, then the square of the modulo of that complex number z2. All right, and you know that the modulo of a complex number gives us the length of a line that connects the complex number to the origin. And since that is the length of the line, it means it's just a line. The square of that is just a line. So by just having the measure of a line, it means that's just a real number. And the conjugate of a real number, it's that same real number, because there will be no reflection about the x-axis. Okay, great. So what that means is that taking the conjugate of this ratio z1 divided by z2 would mean that since they are the same, we are going to take the conjugate of this ratio, which is going to be z1 times z2 bar. We're going to take the conjugate of this ratio z1 times the conjugate of z2 divided by the modulus, the square of the modulus of z2. So we're going to take the conjugate of this. Okay, that's nice, isn't it? Now you notice that from what I just said, that the conjugate of this denominator, of course, is just there. It's just this right here is just a real number. So the conjugate of this fraction will be the same thing as the conjugate of the numerator, which means you're going to have the conjugate of z1, okay, times z2 divided by the square of the modulus of z2. Okay, that's nice, isn't it? Now let's see what we can get from here. Well, this is z2 with a bar. So we've shown already that the conjugate of the product is going to be the product of the conjugates of these two numbers. So in that case, we're going to have this ratio. Let me put the 1 over the bar squared, the z2, the modulus of z2 squared, all right? Then we multiply it by the conjugate of the product is the product of the conjugates. That means we're going to have the conjugate of z1 times the conjugate of z2. Great. So we have that, the conjugate of z2. Now, you notice that the conjugate of z2 is z2 itself from the first property, which we've proven already. That means we're going to have 1 over the square of the modulus of z2. Okay, we multiply it by, well, the z1 conjugate of z1 times z2 itself, since the conjugate of z2 is the z2 itself. Okay, great. So let's see. Well, recall that this denominator here, which is the square of the modulus of z2, okay, is the same thing as, of course, what we had earlier, which is the z2 times its conjugate. We can rewrite this as z1 bar times z2 divided by this right here is going to be z2 times its conjugate, all right, times z2 bar. And you observe that we started by saying that for this to work, the denominator should not be 0. So since z2 is not 0, we can cancel z2 with itself. All right. By that, we get z1 with a bar divided by z2 with a bar. So maybe I'll just clean this part and then we are going to finish the proof off. We are already done. Just that we need to show you that, yeah, we are done. So let's stop right here. Okay, so what we get here is that this right here is going to be z1 with a bar divided by z2 with a bar. That is what we've shown here is that is z1 divided by z2. The conjugate of that ratio is z1 with a bar divided by z2 with a bar. And that's exactly what we wanted to show for the number 7, where the z2 is not 0. So we are done with that. And in fact, we are done showing that each of these properties are true. Okay, so I've told you to do this one, and then you can do this other one where we are talking about the imaginary part of z, which will be the difference between these two complex numbers, the z minus its conjugate divided by 2i. Okay, great, that's nice. All right, okay, thanks for watching. Please share this video with your friends, and we are going to continue with my next video.